Ladies and gentlemen, welcome to lecture number 8. Well, this is the third lecture from the second chapter. And in this lecture, we'll be talking about exponential and logarithmic functions. And then I decided to do another lecture afterwards where I will discuss only problems from this chapter, from chapter number 2, limits and continuity. Okay, let's get started. Well, this is not going to be a long lecture, I assume. So basically, I'm just going to talk about the basic properties of exponentials and logarithms. You will see that that these properties, they're just basic properties. We will see how to operate with exponentials and logarithms, because I would like to use these properties when we will talk about limits and involving exponentials and logarithms, and also continuity, differentiability, and so on. Okay, let's get started. So we'll talk with exponential and logarithm and logarithmic functions. All right, okay. Let's start with the first one. The first one that we would like to start is the exponential function. Okay, so the exponential function basically is this function which looks a little bit like this. It's, let's say, f of x is this number b raised to the power x, where b is a positive real number, and moreover, it's important that it's different than 1. Of course, as you know, 1 raised to any power will give you 1. So the constant is other than 1, and x is a real number. Keep in mind that, right? X is real. So in other words, this function is defined on the set of real numbers, so you can plug in any real value for x, and of course the range will be 0 infinity, so the codomain, whatever. Okay, now so this is how the exponential function is defined. We will see that in some particular cases, for example, when b equals this number e, then we will see that this is a special type of exponential function. And now I would like to start with the following theorem. Let me dive directly into this and say the following theorem. And we'll call this theorem, let's say, bracketing theorem for exponents or exponents. Okay, and now the theorem states the following. Suppose that b is a real number, and let's say that this number is greater than 1, right? Then for any real number x, there is a unique real number b to the power x. So this is important. So, okay, moreover, if p and q are two rational numbers such that p is less than x and less than q. So in other words, these, by the way, that's q over there, is not g. So that anyway, this is how I do my q. So like I was saying, moreover, if we have these two rational numbers such that x is between them, right? We have p less than x less than q. Then clearly we have this inequality. B to the power raised to the power p will be less than b raised to the power x and less than b raised to the power q. This is q here. Okay. So we have this. Well, right? Okay, and now let's graph the exponential function. Okay, and now we'll have two scenarios. The first one is when b is greater than 1. So let's keep this in. We have that the graph will look something like this. It will go through, it will pass through this point here at 1. And the second case scenario is, let me put it, in fact, let me, just a second, let me, x and y. And now the second case is when b is between 0 and 1. So b is greater than 0 and less than 1, so that's, and the graph of this will look something like this. Is y. Again, it will pass through this point 1, but it will look like this, right? So one of them will be increasing, the other one will be decreasing. So that's what it says based on this graph, if you look at it, right? Now let's say that, so f of x is b to the power x, right? In fact, let me put it this way, properties of the exponential functions. Of the exponential functions, just by looking at the graph. So if we look at the graph, and I want you to look at it, right? If we look at the graph, we can, we have the following properties, and the first one is, well, this is, the exponential function is continuous. As you can see, the graph is not interrupted at all for all x. Well, basically, when I say for all x, I mean x between, for all real x, right? The graph is always above the x-axis. This is important. So in other words, let me put it this way, f of x does not have negative values. Okay. Also, we can say that the graph is rising for b is b greater, strictly greater than 1. Well, this means that the function, well, the graph is rising. As you can see, the function is increasing. And also we can say by just looking at the graph that the graph is falling for b between 0 and 1. Okay, so these are the properties, well, by just looking at the graph of the function, right? And now these are the basic facts about the exponential function. And now we would like to talk about logarithmic function. So let's say a few words about the logarithmic function. Okay, logarithmic function. Well, we defined the exponential function, but now I would like to define the logarithmic function. And the way we define it is the following. If b is positive, right, and b is different than 1, the logarithm, right, of x, so we'll to the base b, this is how we pronounce this, is the function, let's say y equals log in base b of x. This is how we this is how we pronounce it. The logarithm of x to the base b, or we can say that y of x is logarithm in base b of x, right? We can say it in this way. So we say that the logarithm, this logarithm is the function y, which is defined as log in base b of x, that satisfies this equation, b to the power y equals x. That is y equals log in base b of x, means b to the power y equals x. So keep in mind this meaning, this equivalence here. This is important. So saying that y is log in base b of x is the same thing as saying that b to the power y is x, right? Okay. Now let's draw the graph, and drawing the graph will tell us a bit more about some of the properties of the logarithm. And let's just say, for example, so the graph of the logarithmic function so when I say logarithmic function, I mean f of x equals log in base b of x. All right. So now the first case will be for b greater than 1. And we have the following. Let's draw the graph. So the graph will be something like this. So this is where it's 1. And it will be something like this. Boom. Right? Then it keeps going. So this is what happens for b equals 1. And now let's look at it by just looking at this graph. Let's say a few things about the logarithmic function. Well, let's see. So let's say properties of the logarithmic function. Keep in mind that we're in this case where b is strictly greater than 1, right? Okay. So now we can say that, well, just like we said in previously, we have the following properties. So we know that this function will be continuous. The graph is not interrupted, as you can see. So we can say that this function is continuous for all x positive. So here x will be belong on this interval. Well, you will see that since my exponential function is defined for all real values, and they will be mapped into all positive real values, the situation for the logarithm is the other way around, is that all values will be will be in 0, infinity, so all values will be positive, and they will be mapped in all reals. And you will see some of these properties. Okay, so it's continuous for all positive values. The graph, we can say something about the graph. The graph is to the right of y-axis, right? This is it. And in fact, we can say here that f of x is undefined for negative values, for x less than 0. So also, the graph is always rising for b greater than 1, right? In other words, the function will be increasing, and the graph is always falling for b between 0 and 1. So these are the properties, the basic properties of the logarithm function. And now let's look at natural base E. Let's see what happens there. Natural base E. So we want to see what happens when we have this logarithm in base E. In other words, this means that B will be this number E. Well, it's a little bit much more to explain what's up with this number, but it appears naturally in well, it appears always when you want to compute the interest, you know, on your bank account and so on. Well, mathematically, it's a little bit strange to define it. Well, it's just the limit of some sequence. So but like I said, it's a very important constant, and it's the basis of many things in math. Anyway, I don't want to get into it, but it's very important, like I said. Okay, and we will encounter this number more often than you think, because it's very important. All right, so what happens in natural base E? Well, here we have, let's say we have the common logarithm. And this common logarithm, let's just say this is, well, okay, is log in base 10 x, or sometimes we'll denote this by, well, it depends, is lg of x, or sometimes it's called log of x. But I prefer this one, lg of x, because log, this will be denoted for the other one, for natural logarithm. So this natural logarithm will be log in base e of x, right, this number e, or sometimes you can say ln of x, or even sometimes, but this will, I hope you're not going to get confused because of this, log of x. So that's why I don't prefer this log of x for common logarithm. I usually prefer for natural logarithm. But anyway, just to keep so that there is no any other confusion, I will denote log in base e of x by ln of x from now on, so that things will be very clear. And now let me explain a bit about this constant. So this constant is called, so this mathematical constant E, which has, it's an irrational number. It's even more, it's a transcendental number, whatever that means. So it's something like 2.71 8.2, 8.1, and you keep going. It doesn't stop. So that's so it's called, well, sometimes people call it Napier's constant, but anyway, let's call it Euler's constant. So this guy Euler, it's a very famous mathematician, one of the mathematical gods. He led the foundation of many, many things in mathematics. He, like I said, he, well, even to this day, people are still rediscovering some of the things that Euler did back in the day. So basically 300 years ago, even more than that. Okay. And now, since I talked about, well, I should have said something about the natural exponential function. So let me point at this as a remark. The natural exponential function. Well, this will be, we'll call this f of x, will be, instead of b to the power x, we'll put here e to the power x, where this e is this Euler constant. Or sometimes we denote this by exp of x. So you will understand that this is e to the power x when I will write it in this way, right? All right, so these are the two functions. And now I would like to talk a bit about the basic properties of how do we operate with logarithm, with the natural log basically, and even with the exponential. Well, with the exponential, I think you know from from college algebra, from pre-calc, how to operate. And now, let's see, properties. Of the, in fact, let's call this basic properties of the natural logarithm. Okay. Like, I want to stress this out. These are very, very important properties because you'll know in what follows, you know how to operate with logarithms, how to add logarithms, how to change base, and so on. The first property that you need to know is that ln of 1, so log and base e of 1 will always be 0. That's always the case. B, ln of e, so the natural log in base e of e will be 1. C, e to the power ln of x will always be x for all x greater than 0. D, ln of e to the power y will always be y for all y. E, b to the power x is, we can write this in this way, it's e to the power ln of b to the x. So we can do this trick, and I'll explain immediately more generally why we can do this. And this will be nothing else than just e times x ln of b for any positive b, and b is not 1. So these are the basic properties. And I want to explain a bit more because I think in my notes is not explained. Let me point out a remark here. More generally, we have the following. Let's say, for example, B can be, let's call this B prime, right? And we have something more general, which says the following: log in base B of B will be 1. As you can see here, if I take B equals E, I recover property number, property B. From then let's say C prime, we have something more general. We have A to the power, or let me put it this way, B to the power log in base B of X will be nothing else than X. Well, if I plug in B to BE, you'll recover the property C. Let's say we have here more general D prime. Let's just say we have log in base B of B to the power Y. Well, guess what? This will be Y. Again, for B equals E, you'll recover property D. And now let's see E prime. We have, well, here I don't think we have this. It's exactly what we need. The only thing is that we can write this. In fact, okay, let me write it more general. We have that B to the power log in base in fact, this is covered by the second one. So anyway, you can write this in any base. So we can write B to the X. Oh, B to the X. You can write this as log in base A of A to the power B to the X, right? And here, this will be nothing else. Well, anyway, I don't, it's okay. You don't need to. Okay, because E is already written in its more general form. So, right? Okay. Now, so these are the main properties, the basic properties of the natural log. But now, let me say, how do we change the base? So this is a special property. Let's put this F here, is the change of base theorem, which says that log in base B of X is nothing else than ln of X. So we change the base to base E over ln of B. So for any positive B and B different than E. So we call this change of base theorem, or change of base formula, let's say. Right? So this is how we change the base. You can, now you see, we changed this to base E, but you can change it to any base you want. You can change it to base 10, you can change it to base 2, and so on. The only thing, so this is change of base formula to base E. Let me be specific. For example, you can change to base 2. You can have something such as B log in base B of X will be nothing else than just log in base 2 of X over log in base 2 of B. So this will be, we'll call this change of base formula to base 2. And you can play with this. You can change it to any base you want, right? Now let's put them together. Let's draw, we'd like to draw a chart, and we'd like to put all these properties together, and we'd like to see how we distinguish between them. And then afterwards, we'll do some examples. Let's call this basic properties of of exponential and logarithmic functions. Okay, let's draw a chart here. And we'll do it in the following way. Okay, here we go. Okay. Now here we're going to have a rule. Here will be the exponential function. Here will be the logarithmic function. So, and here I will now say the exponential function, a and b, that the numbers that we will use are positive numbers. And here, b will be positive and will be different than 1. Okay. All right. So let's start. The first one is the equality rule. And let's see what's going on here. So for the exponential function, we have that b to the power x is the same equals b to the power y, if and only if. So when I put this if with double F, I mean that this is if and only if x equals y. Well, in other words, the exponential function is 1 to 1. So this happens when b is not 1. The same thing happens for the logarithm. So we have log in base b of x is the same as log in base b of y. This happens if and only if x equals y, right? Okay, so this is the equality rule. Now let's see what happens for the inequality rule. For example, if x is greater than y, right, then b of x, it'll be greater than b of y, right? We have this. In other words, the function is increasing. For b greater than 1, and we have the other way around, the function will be decreasing. So b of x is less than b of y for b between 0 and 1, right? And now for logarithm, so in the inequality rule, if x is greater than y, then we have the following. Then we have that the logarithm in base b of x is greater than log in base b of y, right? For b greater than 1, and log in base b of x is less than log in base b of y for b between 0 and 1, right? These are the inequality rules for the exponential and the logarithm. Well, it's quite clear that if the base is greater than 1, then the logarithm function is increasing, and if the base is between 0 and 1, then the logarithm function is decreasing. Now let's see what happens when we have the product rule. And here we have the following, b of x times b of y. So when we multiply two exponentials, well, guess what? The base will stay the same and we'll add the exponent. So this rule, you already knew it from pre-calc, I'm pretty sure. Well, for logarithm, the situation will be a little bit different. So log in base b of xy will be nothing else than just, so this will be equal to log in base b of x plus log in base b of y. Right? Keep in mind this rule. This is how we operate with logarithms. Okay, now let's see what happens when we have the quotient rule. Well, here we'll divide two exponentials, so we'll have b of x over b of y will be nothing else, so the base will stay the same, and we're going to subtract the exponent. So that's how we're going to, again, you already knew this rule from pre-calc. And as for the logarithms, we have the following: log in base b of x over y. This will be nothing else than just log in base b of x minus log in base b of y, right? Now the power rule says the following: we have b of x, b to the power x, everything to the power y, will be nothing else than just b to the power x times y, right? Or also, if you want, we have more. If we have a, b, everything to the power x will be nothing else than just a to the x times b to the x. And also, we will have, if we divide a and b, we'll have a over b to the power x will be a to the x over b to the x. And also, we have here log in base b of x to the power p, let's say. This will be nothing else than just p log in base b of x. For any real number p. Okay. In fact, let me write in words here. For any real number p. Okay, now we have two more rules. So let's say inversion rule. And here, well, we don't have anything for exponential, but we have for logarithms, b to the power log in base b of x will be x, or log in base b of b to the power x, let's write it in this way, will be again x. And also, we would like to see what happens to some special values. Well, for exponential, we have e to the power 0. Well, this is obvious. But in fact, b to the power 0 is 1. And let's say 1 to the power x will be 1. And here, log in base b of b will be 1. And log in base b of 1 will be 0. All right, I think this sums up pretty much the properties that we, the basic properties for the two functions. And now in the remaining time, I'd like to do some applications, right? So let's do some examples. And let's start with the first one. Solve the following exponential equation. All right, let's see. Let's say part A. We would like to solve the following. 2 to the power x cubed plus 3 is the same as 16. The second one will be B. Let's say square root of 2, everything raised to the power x squared will be equal to a to the power x over 4. All right, so let's solve these two. Well, let's look at this. Let's look at the first one. So I have 2 to the power x cubed plus 3 equals 16. How should I solve this? First of all, as the problem states clearly, this is an exponential equation. We should solve it. So the way we should solve it is that maybe we can write that 16 as an exponential, right? Maybe we can write this as 2 to some power. And yes, we can do it. So the equation 2 to the power x cubed plus 3 equals 16 can be rewritten as the following. 2 to the power x cubed plus 3 is the same as 2 to the power 4. But now, guess what? By applying the equality rule, so by the equality rule, what do we have? Well, the base is the same, as you can see. So 2 is the same as here. So this means that the exponents have to be the same. So by the equality rule, it follows that x cubed plus 3, is equal to 4. So x cubed is the same as 4 minus 3, which is 1. So from here, it follows that x equals 1. And that's it. Now let's see the second one. So again, the equation, let's rewrite the equation. The equation, square root of 2, everything to the power x squared equals 8 to the x over 4. Let's rewrite this. Can be rewritten as, how can we rewrite this? Well, square root of 2 is 2 to 1/2, so we can write this in the following way: 2 to the power 1/2, everything to x squared equals 8 to the power x over 4. Or we can write this in the following way: 2. Now we apply the power rule. This will be 2 to the power 1/2, everything to the power x squared will be 2 to the power x squared over 2, because it's x squared times 1/2, which is x squared over 2, equals 8 to the power x, everything over 4. Okay, now let's keep going. Or equivalently, let's multiply by 4. 4 times 2 to the power x squared over 2 equals 8 to the x. Or we can write this 4 as 2 squared times 2 to the power x squared over 2 equals 8 to the x. And now, as you can see, we have the same base here, 2. So I will add the exponents. So this will be equivalent with 2 to the power x squared over 2 plus 2 equals 8 to the power x. Well, but we have to do something. As you see, I have 2 to some power is 8 to some power. They don't quite look the same yet, but maybe we should do something about it. And indeed, we can do it. Maybe we should rewrite that guy 8 to the power x in a certain way. This guy, we should rewrite this guy. And we have the following, or 2 to the power x squared over 2 plus 2 will be, and pay attention now, 8 will be 2 to the power 3, everything to the power x. Or equivalently, I can swap these two. So this will be 2 to the power x squared over 2 plus 2 will be equal to 2 to the power now 3x. Great. So I reach all the way up to this point. which is absolutely beautiful. As you can see here now, I can apply the equality rule. So by the equality rule, we have that, well, as you can see, these two have the same base. So we will have that x squared over 2 plus 2 is the same as 3x, right? Well, let's do some computations here. So this will be equivalent with the following equation. Well, if you do all these computations here, this will be with the quadratic equation. Let's just say this would be x squared minus 6x plus 4 equals 0, right? And again, you can solve this, solving this equation. I'll leave it to you as an exercise, solving this equation. So you know how to solve a quadratic equation, I believe, by now. And I hope you do, because this is a prerequisite for this course. Solving this equation will give us the following two solutions. We get the following solutions. So the two solutions, x1 is 3 plus square root of 5, x2 will be 3 minus square root of 5. Anyway, this is how we solve this. Okay. Now, let's see some other examples. So this was the first one. The second one. Solve the following equation. The following equations. And you'll see the first one is, let's say 2 to the power x is 21. And the second one is, let's say 3, because I would like to write this in a logarithmic way. Let's say 3 to the power, let's say 2x minus 5 equals 4. Okay. Let's see this. All right. Well, let's look at the first one. Well, as we have previously seen, the first thing that we would like to try is to make that guy 21 look like 2 to some power, but unfortunately we cannot do this. 21 is 7 times 3 is the product of two prime numbers, so there is no way we can make it look like this. So what we're going to do is the following. We're going to take the logarithm. So take the, let's say, well, basically it's just the property. So 2 to the power x equals 21. By the way we define the logarithm is equivalent with saying that x is nothing else than just log in base 2 of 21. And that's it. This is the number that verifies this equation. So this exponential equation. So don't be surprised if you write the solution in terms of logarithms. So the same story will go for the second one. Well, here we would like to, unfortunately, we cannot write 4 as 3 to some power. There is no way we can do it. Well, we can do it, but in terms of logarithm if you want. In fact, let's write it in this way. So the equation, we could have done it with the first one as well, but 3 to the power 2x minus 5, sorry, equals 4 is equivalent with what? Well, this 4, well, can be written in this way. And let me put it this way. 3 to the power 2x minus 5 is the same as 4 to the power 1 or we can write this 4 to the power log in base 3 of 3. But we can, there is a property that I should have mentioned this. Anyway, I'll mention it here. That, so property of the logarithm which says the following. I'm going to write it big here. A to the power log in base A of B. Well, actually, I mentioned this, but anyway, is nothing else than just, okay, C. Let me put here number C. Is you can swap these two. So it's the same as C to the power, in fact, okay, let me write it in this way. So that all of them are A to the power log in base B of C. So we can swap these two. So A to the power log B of C, we can swap these. It will be nothing else than just C to the power log in base B of A. So B will stay the same. So this is the property, and we can apply it in our case. So as you can see here, this guy will swap this with this, which will be 3 to the power log in base 3 of 4. Well, now, as you can see, now we have that 3 to the power 2x minus 5 is the same as 3 to the power log in base 3 of 4. As you can see now, the base is the same, 3 and 3. So by the equality rule, it follows that two x minus 5 is equal with log in base 3 of 4. Well, and now if we do some algebra, which gives us it will give us the following, that x will be nothing else than just log in base 3 of 4 plus 5 and everything over 2. Right? Okay, so this is how we solve. Now let's see another one. Let's solve another one. 3. Solve the following equation. The following equations. And the first one that we have in mind is the following. So I'm just going to do a logarithmic equation, and then, in fact, yeah, and then I'm going to do an exponential one. In fact, let me separate the two. Just solve the equation. And the example that I have in mind is the following: log in base 3 of 2x plus 1 minus 2 times log in base 3 of x minus 3 is 2. So look at this equation. As you can see, it's a purely logarithmic equation. Well, in this equation, we'll have to apply the properties of the logarithm. And we'll try to make our life as easy as possible. So let's see. Let's look at the equation. As you can see here, let's identify something first. As you can see, have the same base. Both logarithms are in base 3. So we know that there are some properties with logarithm in the same base. You can add, you can subtract, right? So the product or the quotient rule. As you can see here, I have the difference between the two. So maybe I should apply the quotient rule. But there is a problem here. I have this guy too here that gives me a bit of a headache. So this guy here. Maybe I should do something about it. Well, what we can do is the following. We can so we know that log in base b of a to the power x, let's say, right, is nothing else than just a. So ax will go here in front of the logarithm, is nothing else than just x times log in base b of a. So maybe we should apply this property. So our equation is equivalent with the following. Log in base 3 of 2x plus 1. And now we apply this rule. So this will be minus log in base 3 of x minus 3 squared, right, equals 2. And now we can apply the quotient rule for the logarithms, right? So this will be equivalent with log in base 3 of 2x plus 1, everything over x minus 3 squared, right? And this will be equal to 2. All right, so we reach all the way to this point. So what should we do here? Well, it's quite clear. We know that log in base b of x is y. So this means that what? This means that this guy is 3 squared, right? So this implies that what? That 2x plus 1 over x minus 3 everything squared is nothing else than just 3 squared, which is 9. And now let's do some computations here. So we have the following. 2x plus 1 is the same as 9 times x minus 3 squared. Or if we do all these computations, we expand this, and this will be equivalent to with the following, with 2x plus 1. And at some point, after we expand all this guy, this will give us 9x squared minus 54x plus 81, sorry. Or we will have that 9x squared minus 56x plus 80 equals 0. Or equivalently, x minus 4 times 9x minus 20 equals 0. And the solutions are the following: x equals 4 or x equals 20 over 9. And now we can check these two answers, and you'll see that x equals 4 is a solution. And now let's see what happens when x equals 20 over 9. So we should check these two answers. So for x equals 4, let's see the first one, x equals 4. Let's see what happens here. So we'll have that 2x plus 1 equals 9, which is positive, right? And we also have that x minus 3 equals 1, which is positive indeed. So x equals 4 is good. So it is a solution. But now let's see what happens with the other one. So we always need to check these solutions. Keep in mind this. Let's see what happens when x equals 20 over 9. So in this case, we have that 2x plus 1 equals 40 over 9 plus 1, which is positive, so no problem. But in this case, x minus 3 is 20 over 9 minus 3, right? This will be negative, so this is undefined. Well, we can say that, so x equals 20 over 9 is not a solution. So the only solution is x equals 4. And that's it. All right, now let's see some other problems that we like to solve, and probably we'll stop here afterwards. So this was 3, now 4. Solve the following equations. The first one is, let's say cube root of 2, everything to the power x plus 10. This will be equal to, let's say, 2 to the power x squared. So that's the first one. The second one is e to the power 2x plus 3 equals 1. And c, e to the power x squared over e to the power x plus 6 is 1. All right, so let's look at these three equations. They look a bit in a, I would say in an unpleasant way, but well, not the second one though. The second one actually looks very nice. But well, they're not hard to solve, but I would like you to look at them for a couple of minutes, well, for a minute or two. All right, let's see. Let's see the first one. Well. We should do something about it. You see, you have that cube root of 2 over there, so maybe we can rewrite this in a certain way. So let's write this cube root of 2, everything to the power. Okay, so write cube root of 2, everything to the power x plus 10 to be equal to 2 to the power 1/3, right? Because we can write the cube root in this way, everything to the power x plus 10. And this will be equal to 2 to the power x plus 10, everything to over 3. And this guy, so the equation is equivalent with the following: 2 to the power x plus 10, everything over 3, will be equal to 2 to the power x squared. Right? So as you can see now, we can apply the equality rule that have the same base. So by the equality rule, we have the following. We have that x plus 10 over 3 is the same as x squared. So 3x squared is the same as x plus 10, or 3x squared minus x minus 10 equals 0, right? Or we can write this in the following way. Well, we can solve it using the quadratic formula, but I'm lazy in doing that, so we'll just factor this. This will be x minus 2 times 3x plus 5, I think, equals 0. The solutions for this